Okay, we're going to keep looking at parallelograms, but sort of from a different perspective, like working backwards by verifying that certain quadrilaterals would have the properties of parallelogram to verify that they would be. So there's some deal breakers. If we have both pairs of opposite sides parallel, right, both opposite sides, in this case AB and DC, would be one pair. The other pair would be AD and BC. Okay, if those pairs of opposite sides are parallel, both of them, then we have a parallelogram. In the same regard, if both pairs of opposite sides are equal, we have a parallelogram. Okay, or both pairs of opposite angles are equal, we have a parallelogram. Or if we have diagonals bisecting each other, we have a parallelogram. And the last one I want to point out, if I have one pair, just one, all I need for this rule is one pair that's equal and parallel. If it's both, then we also indeed would have a parallelogram, so we can use those. And what I want to do is apply these rules to quadrilaterals that we have on the graph. If they ask us to use the slope formula to verify that we have a parallelogram, then we're going to be looking for opposite sides to be parallel, and we need both pairs to be parallel. So the very first thing we would have to do is plot the 4 points. I have the point at A, 0, 0. I have a point at 1, 3. That's B. C is at 5, 3. And then finally D is at 4, 0. So if I wanted to use the slope formula to verify the parallelogram, I'm going to look at this side BC. The slope of that is 0. It's a horizontal line. The slope of AD is also 0. So here I have one pair of opposite sides that are parallel because they have the same slope. Now I go and look at the other two sides. This line here from A to B goes up 1, 2, 3, and over 1. So that is a slope of 3 over 1, and this one goes up 1, 2, 3, and over 1 as well. So here we can verify that we have a parallelogram because both pairs of opposite sides are parallel. I'm using the slope formula for that. Let's try the next one. This time I have D at negative 1, 1. So again, we have a couple of easy slopes here because they're horizontal lines, so that slope is 0. That's easy to verify that that's parallel. But now I have to check the other slopes. From D to E, the slope of DE is up 1, 2, 3, and then over 1, 2, 3. So that's a slope of 1. Right? Up 3 over 3. Over here we go up 1, 2, 3, and over 1, 2, 3. That's another slope of 1. 3 over 3 is just a slope of 1. So here we do have a parallelogram. I'm showing both pairs, opposite sides, are parallel. So notice the directions in this one are distance formula, and this one is distance and slope. So these are going to be a little bit different. But first thing I have to do, of course, is plot the points. So we start at R, which is at negative 1, 0, right there. So these are my 4 points, and what I want to do now is use the distance formula to see if we have a parallelogram. So how would we use the distance formula? We would obviously find the lengths of each side, and this is not looking much like a parallelogram to me, but I'll start with the easiest side to find the distance for, and that would be just RS because it's right along the straight line. It's just 1, 2, 3, 4. So that has a distance of 4. So in order for this to be a parallelogram, this side opposite would also have to be a distance of 4, okay? And from the looks of it, we don't have a distance of 4. We have, remember using Pythagorean theorem here, that's a distance of 1, and then a distance of 1, 2, 3, 4, 5, right? So this is going to be 1 squared plus 5 squared, and we would take the square root of that. So this is going to be the square root of 26, which obviously is not 4. So we can say this is not a parallelogram. And I don't need to verify the other opposite sides because I already know I have one pair that are not equal to each other, but I would do the same thing. I'd use the distance formula here, and this would be the square root of 2 squared plus 2 squared. Over here, this would be the square root of 1 squared plus 3 squared. but we don't have a parallelogram, so we can move on from that one. Okay, so now we're going to team up slope and distance. So basically I'm going to look at one pair of opposite sides and see if they have the same slope and the same length, and that would verify that we have a parallelogram. So I'm going to go plot my points. A is at -3, 2. So remember, since I'm going to use slope and distance, I'm only going to focus on one pair of opposite sides. All right, so I'm going to go ahead and focus on this side AB and this side DC. And I'm going to verify that they have the same slope and that they have the same length. So let's do slope first. The slope of AB. Okay, we go up 1 over 1, up 1 over 1. It's a slope of 1 over 1. For DC, we'll verify our slope. We go up 1 over 1, up 1 over 1, or we go up 2 and over 2. Either way, it's a slope of 1 over 1. So we're good on slope. Now, if we just wanted to use slope, we would go and verify the slopes of AD and BC. But we're going to use distance now. So the length of AB, if we use our Pythagorean theorem, we have 2 this way and 2 this way. So it would be 2 squared plus 2 squared. And we take the square root of that. Okay? And we see the same thing happening down here. We have a leg of 2 and another leg of 2, so that distance would be 2 squared plus 2 squared, and we will take the square root of that. Okay? So for our distance for AB and DC, we see we have, this would be the square root of 4 plus 4, or the square root of 8. And this is also 4 plus 4, square root of 8. And I don't have to calculate that. I can see that they're the same. So we can just leave it as the square root of 8. And what I've shown now is that one pair of opposite sides is both parallel and congruent, and that means that we do have a parallelogram. So number 5, we're going to do the same thing again. It's distance and slope. So we'll focus in on one pair of opposite sides. So we start with S is at -2, 4. So it's up to us really which side we want to verify this with. I'm going to look at SV and compare that to TU. And remember, I'm going to do both distance and slope. So we can do slope first. In order to move from S to V, it looks like I have to go down 1, 2, V is right here, 1, 2, 3, and over 1, 2, 3, 4. So SV has a slope of -3/4. So I'm going to compare that to TV. I'm sorry, TU. Can't read my own writing here. That's a U. So from T to U, we have to go down 1, 2, 3, and over 1, 2, 3, 4. So it looks like our slope checks out for us, okay? And now we need the distances to check out as well. So my distance for SV and my distance for TU. So from S to V, if we look at our triangle for a distance formula, we would have 3 squared plus 4 squared. Okay? And that's a famous Pythagorean triple, 9 plus 16. This is the square root of 25, which is 5. And then for T to U, same thing. 1, 2, 3, 1, 2, 3, 4. So we would have 3 squared plus 4 squared, and we'd take the square root of that. So we do indeed have a parallelogram here. And the last one says midpoint formula. So this is something different than what we've done so far. We haven't used midpoint formula. When we think about how would we use midpoint formula to verify that we have a parallelogram? And the answer to that is going to be our rule that the diagonals bisect each other. So think about that for a second. If I have a parallelogram, I know that the diagonals bisect each other. What does that mean? Okay. It means that these two diagonals have the same midpoint. If they bisect each other, then they have the same midpoint. So what I'm going to focus in on this parallelogram is going to be the diagonals. Instead of looking at opposite sides, I'm going to look at the diagonals and see if they both have the same midpoint. If they do, then I have a parallelogram. So let's plot F first is at 3, 3. G is at 1, 2. So we can kind of tell right away this is not a parallelogram, but we want to verify it with the rule. So I'm going to look at the diagonal IG and its midpoint, and I'm going to look at FH and its midpoint. Those are my two diagonals. I drew them in up above here, and you can see. So the midpoint of IG, if I were to calculate that, would live at -1. We take the x-coordinate of I, which is -1, plus the x-coordinate of G, which is 1, and divide by 2. Then we take the two y-coordinates for I and G, which would be 4 and 2, divide that by 2. So I'm going to get 0 and 6 divided by 2. I get 0 and 3 for my midpoint of IG. And now I want to try to verify if FH has the same midpoint. About the midpoint of FH, I'm going to take 3, the x-coordinate for F, and -3, the x-coordinate for H, and we'll divide that by 2. And then I'm going to take the y-coordinates, which for F is also 3, and for H is 1. I'm going to add them together and divide by 2. So I do get the same x-coordinate, looks like. I get 0 divided by 2, but then I'm going to have 4 divided by 2 here. So my midpoint here would be 0 and 2. And we can see in our graph here that it doesn't look like these 2 points. This is I think that's the midpoint for one of them, and this is the midpoint for the other. They don't intersect at their midpoint, so the diagonals are not bisecting each other. So this is not a parallelogram, and we have the math to back it up.